our lecture on heat treatment of steel. This is the third lecture. So far what we have seen is we saw that several types of heat treatment can be given to steel because of certain specific characteristic of iron carbon system, and we looked at the time temperature transformation diagram. So, phase diagram also has an important feature, and there are three distinct different types of reactions that take place. Some are isothermal and some are athermal. Like we talked to about Pearlitic transformation, which is an isothermal transformation, and other extreme we looked at martensitic transformation, which is a thermal transformation. We also looked at isothermal transformation kinetics, which is actually a process where you have simultaneous nucleation and growth of the transformation product. We discussed this with respect to eutectoid steel. Eutectoid steel. But the process kinetics will be very much similar, and in other case hypo or hyper eutectoid steel also we will look at what happens. In all heat treatment process, first stage will be austenitization. We will also look at partly this, and today we will also, there are certain characteristic of martensitic transformation which is worth recalling. These are the two extreme kind of transformation that takes place. Here Pearlitic transformation, you have a very long range diffusion, and this is controlled by nucleation and growth. In other extreme case, here there is no diffusion, it is diffusionless transformation. We will see how does this take place a little more critically today, whereas Bainitic transformation has certain features which match with Pearlitic, certain features morphology which matches with martensitic. So, I mean, but basically here some precipitation does take place. So, Bainitic transformation is a transformation where some amount of short range diffusion of carbon atom is essential, that is the key. And today we will also look at some of the common heat treatment, commercial heat treatment, annealing, normalizing, hardening, and we will also see all hardened structures are given a subsequent heat treatment called tempering. And to know these commercial heat treatment, it is also necessary to know about a diagram called continuous cooling diagram, because most commercial heat treatment process you will not be transformation will not take place at a constant temperature, you will be cooling the sample continuously. Now, let us a quick recapitulation of the three different types of transformation which takes place: Pearlitic, Bainitic, martensitic. This we looked at their structures. This is lamella. Here you have two variant, lath plus cementite, another lower temperature bainite. They are nearly acicular or plate type, and where carbides may be cementite, or in cases they can be epsilon carbide. Here we are considering, say, this is written specifically for 0.8% carbon steel, eutectoid steel, where the martensite will be primarily acicular or plate type martensite, it is single phase, whereas in these cases they are two phase structure. So, this clearly shows that there is no precipitation, no diffusion. So, in this case, as we mentioned, long range diffusion, bainite, short range diffusion, here there is no diffusion. This is isothermal, this is also isothermal. We can say this is a high temperature eutectoid reaction, this is you can say a little lower temperature eutectoid transformation, but this has also isothermal character, whereas martensite transformation is athermal. Now, whenever transformation takes place, the precipitation in certain cases they take place on particular plane, which is known as a particular plane of the matrix, and this is called orientation relationship. In case of Pearlite, cementite can form on there is no definite relationship on which plane cementite will form, but in Bainite there are definite relationships, and in fact these relationships can vary with the morphology. Lath will have one kind, acicular or plate type structure will have another kind, and similarly martensite also forms on definite crystallographic plane. So, this also has a definite crystallographic relationships. So, intermediate product Bainite has certain character which matches with martensite, certain character which matches with austenite. Now, last class we talked about how the deformation takes place in a martensitic transformation takes place. When you are quenching, that at the temperature from which you quench, at that temperature structure of steel is austenite, which is face centered cubic structure, and you have some carbon atom, and number of carbon atoms, even if you have 1 atomic percent, mind you. So, there may be in one unit cell, I mean maybe a collection of unit cell, if you have 50 atoms, there will be 1 atom of carbon. So, number of carbon atom with respect to iron is very less, and this carbon atom occupies octahedral sites, and which is shown over here. Say look at these octahedral, these are two neighboring face centered cubic cell which are shown over here, and these interstitial atoms, they will be present at these octahedral sites. So, like this, one common octahedral site is the center of the face centered cubic structure. So, these are the octahedral sites, but mind you only one in every 50th atom will be a carbon atom. Now, whenever this atom is present, this distance is smaller compared to distance in an in a BCC lattice, you will find that this distance in FCC it is symmetric, it is same in all direction, that octahedral site, but when it transforms to a BCC, it has to contract in this direction. So, which is shown over here. If A is the lattice parameter of austenite, which is of this order, this is the lattice parameter of austenite, whereas lattice parameter of ferrite is around this. And look at it at very low carbon concentration, that martensite can be almost considered as a BCC, and look at how a BCC structure can form over here. So, look at this cell which is drawn here, this particular cell. Here you have a center atom here, you have a center atom which is iron atom. So, this is an iron atom at the center of this lattice, and but this dimension, if you look, this dimension is A, whereas A is the lattice parameter of austenite, and whereas this dimension, which becomes one of the say either A or B of the BCT or BCC lattice. So, this is actually A over root 2. This also is half the diagonal, this also is same, this as well as this. So, therefore, you just same thing is drawn over here. So, this is A over root 2, this is A. So, this is not a BCC lattice. To make it BCC, what you have to do, look at this, this is much larger than this dimension. So, what you have to do, you have to compress it in this direction, and A over root 2 is less than this value, and you have to expand in this direction. So, you will have to transform this unit cell to a martensite unit cell, you have to give this kind of deformation, 20% contraction along the z direction or along the c axis, and it will expand 12% along this direction, expansion, and this directions you have to have contraction. And then these lattices this becomes equal to this, nearly equal. If you have carbon atom, we will see later, there will be this will be in, if you have high amount of carbon, then this lattice get distorted, it is body centered tetragonal, but which is very close to this C by A ratio, this axis becomes C, and this will be close to, I mean not very much different from 1, depending on carbon content, it can be 1.05 or 1 around something, which is actually very nearly you can say it is a BCC structure. Now, if this type of transformation takes place, then there are set crystallographic restrictions which must be followed. And look at this, this is shown in this next slide. Here look at this, this is the cell in the previous diagram, which gets converted into a body centered structure. Now, look at the correspondences of different planes and directions in this case. Now, here try and find out what is this plane. It intersects here at unit distance, here at unit distance, here of course, you can extend it here. So, this plane, if you extend, it is something like this. So, this plane, which is known as numbered as named as A B C, this plane is actually a 1 1 1 plane, and this is a plane in austenite lattice. Now, you look at this, when it becomes transformed into a martensite or BCT or nearly a BCC structure. So, this plane, this A here is A prime, B here is B prime, and C here is C prime. Now, look at this, and then you can easily see that this plane, now what is its indices? So, it is parallel, what you can see, it is parallel to the x axis, it is parallel to, it intersects z axis at 1, this is, it intersects this axis at 1. So, it is a 0 1 1 type of plane in ferrite or martensite. So, that means this plane and this plane, this plane and this plane, they will have a close relationship, and in fact, this is called the habit plane. In one particular case, we can say this plane is parallel to this plane of a cube, a particular this is octahedral plane 1 1 1 plane on austenite is equivalent to 0 1 1 plane in martensite. Similarly, there are directions also, you can try and find out this direction. So, look at this direction, this will be a direction, I am not marking these signs which you you try and find out what will be the exact directions, but this will be a direction of 1 1 0 type, whereas this will be a direction, this is two places, two see half unit along, say to reach from here to here, you move 2 units along z axis, half along y, half along x axis. So, this particular one is a 1 1 2 type direction, and if you try and find out this angle will come out to be around 30 degree. Same thing you do over here, find out this. So, this is, what is this? This is a 2 diagonally placed points are joined. So, this is a 1 1 1 type directions, whereas this is a 1 1 say 0 1 1 direction. So, if you find out the angle between these two, it may not be exactly this, but it is within close. So, this you may find this is around 35 degree. So, crystallography, these planes are almost similar, and I leave you as an exercise to for you to find out these indices. So, this direction in austenite will be parallel to this direction in martensite. Now, the question comes is how does this kind of homogeneous Bain distortion can take place in a lattice. So, Bain distortion is a homogeneous distortion. What you are trying to do? You compress the lattice in the c axis, expand in say z axis you are compressing, you are expanding, pulling it along x axis, pulling it along y axis. So, this is a homogeneous deformation, and in this case are there any undistorted plane or undistorted directions. And to understand this, if you look up I mean try and construct in 3D an isometric view, this is the x, y, z axis, and you have considered a sphere. So, this is 1/8 part of a sphere, which is, and now suppose you are compressing the sphere along z direction. So, from here it comes to this point, this is let us say z star. Similarly, x you compress here, this goes as x star, y you compress from here to here, it becomes y star. So, now you construct this surface, what you find, these two surfaces they will meet along this curve. So, this is a plane on which it meets. So, any direction on this cone, say like O is the origin, OA, OB, or any lines here which is lying on the cone, these directions are unchanged directions. But here whenever a slip process takes place, or certain deformation processes takes place, certain planes remain unchanged. Like in case of a slip, when a slip is taking place, the slip plane remains undistorted, lattice around that gets distorted, but the slip plane remains undistorted. Similarly, when twinning takes place, a part of this above the twin plane is just slightly gets tilted, so that this becomes a mirror image, that part top part becomes a mirror image of the bottom part. So, this is the kind. So, here also you will find the twin plane, any direction line you draw, the twin plane is undistorted, but other anything you perpendicular and other directions they rotate. So, same thing what you find over here, when you have a homogeneous deformation, you have only certain undistorted directions. You cannot think about an undistorted plane. Now, in order that say suppose this Bain distortion, so that means Bain distortion is a severe distortion, how will this be accommodated in the lattice? So, we know that crystals can undergo, if you have applied too much, if there is a too much of distortion or too high a stress, the material deform, its shape changes either through slip or through twin. Now, the question comes, is there a possibility, say suppose look at the same thing, this is here we have drawn a projection, looking from this direction, you look at it from this particular along the y axis. In that case, this is the sphere which is undistorted. Now, you have compressed it along, and in that case that y point will be projected at the center. This is the origin also, and y will be located at the origin here. Now, imagine that this has compressed along this direction, and x direction it has expanded. Similarly, and the y which is perpendicular to this plane, here also there is an expansion. Now, look at this here, these directions, these points of intersections, any line passing through, actually this will be formed in a 3D, it will be a cone, and anything which is passing through this point, that cone. So, these are undistorted directions, but we can't think about an undistorted plane. To get an undistorted plane, what you have to do? You have to find, say, suppose one of the y plane which intersects here, say this is y is perpendicular like this. So, in any plane which is passing through this, suppose you rotate it through an angle theta, then it will match with this. So, that means you can think about an undistorted plane provided you allow certain amount of rotation in the crystal lattice. So, that means to accommodate Bain strain, it is in the crystal lattice, you have to visualize some kind of rotation of a part of the crystal in the lattice. So, what it means that homogeneous Bain distortion, this has unchanged directions, but has no undistorted plane. And so, therefore, to accommodate that kind of a deformation will be extremely difficult. So, the crystal will deform, and this deformation can be, through that it can relax the stresses, and this is possible through two processes. One is slip, and we have seen earlier slip is a simple shear process. So, it is actually which is made up of, there is some amount of rotation involved. Another is twin. Now, slip can take place through dislocation glide, whereas twinning, some kind of a lattice rotation. Now, in this case slip, you have say several planes, if you have a slip plane, say this is one plane, you can think of several packets here. So, each can slip like this. So, these bands they slip over the other, whereas in case of twin, the atom moves a fraction of an atomic distance, and on each plane that atom moves the same distance. So, that is twinning. So, through this it is possible to accommodate Bain distortion in the crystal lattice, and with this it is possible to explain, actually through slip it is possible to explain one kind of a that crystallographic relationship it is possible to explain, because deformation, the slip can occur on specific planes, say like slip plane in a face centered cubic, it is 111, BCC the slip can occur on 110 plane. So, that way, I mean there are certain so which can explain that crystallography of transformation, and depending on which method, whether this Bain distortion is accommodated by slip or twin, we have two different kinds of a martensitic structure. This gives, the present name is a lath martensite, whereas this gives plate type of martensite or acicular martensite. And now, crystal structure of course is a function of carbon content, which is shown over here. What is the effect of carbon content on lattice parameter and hardness martensite? Now, look at this. If it is austenite, lattice parameter increases almost linearly with carbon content, whereas if you increase carbon content in the say in martensite, you will find its C axis increases with carbon content, whereas A keeps decreasing with carbon content. So, on the whole it is the C by A ratio which increases with carbon content. So, higher carbon content, there is a more lattice distortion, so more local strain. So, therefore, they have higher strength apart from the solid solution contribution of carbon. So, martensite, what you have is a deformed structure, highly deformed structure, either plastically deformed or a twin structure, and which is submicroscopic. it is very extremely difficult to see the plates or that fine structure of the plates or the lats. You can see it only under transmission electron microscope, and the dimension of the lath etc., the lath or plate that interplate spacings, they are of nanometer dimension. It is say distance may be several atomic layer, say 8 to 10 atomic layer. So, it is actually a nanostructure. Now, fine structure is a nanostructure, can be seen only under electron microscope, and such fine structure definitely is associated with increased hardness, which reflects over here. And if you measure the hardness against for different carbon containing martensite, you will find there is a relationship of hardness measured on the Rockwell scale. It follows a plot like this, and somewhere around 0.6% carbon, it almost that increase is not significant, but nevertheless Rockwell scale is not linear. So, maybe you measure in weaker scale, you will find that even beyond 0.6 the hardness of martensite can increase. Now, a quick look, we looked at the martensitic transformation in little detail about the crystallography, which has an effect on morphology, which is shown as, see, one class is lath, which forms because of dislocation movement or through slip. Slip is the main mechanism, and these are the slip bands what you can see here. These are slip bands which you can see, it is an exaggerated view. You can see this fine structures within these laths only under electron microscope. So, these are the kinds of structure, and it has a rational, I mean, habit plane, and this type of structure forms in low carbon, relatively low carbon steel. And this is present name is lath, but it has been known by several other names earlier also, which is shown here. And other one, that where you have irrational plane, it is a needle like structure, and this is the structure, and in this case this interface movement, whether it is lath or whether it is plate type martensite, this is very fast. This moves almost at the speed of sound. So, therefore, if in theory, see, it should emit or it should emit acoustic noise, and which can be audible, I mean which is in the audible range, and in fact, of course, it get masked by certain other signals, particularly since you are quenching, there will be certain other noises also, but it is possible to filter out those noises and also monitor the noise that comes out from formation of this martensite plates or laths. And in this particular case, if you have a twin martensite, which is commonly known as plate type, here the habit planes are irrational. It can be either this or this of forms on these planes of austenite. Now, when such a fine structure forms, often it may be, I mean, we applied the principle of thermodynamics, and this has been applied to martensitic transformation as well. And we know that two phases, say high temperature phase is austenite. If you plot the free energy of austenite, which is shown over here, free energy of austenite and free energy of ferrite. So, this is ferrite, the free energy of austenite. So, above a particular higher temperature, austenite is more stable. As you cool down, somewhere in between austenite and martensite, maybe both may have same free energy. This temperature is known as T0, and MS temperature is shown here. Now, two things are happening when a martensite needle of a plate forms. It is associated with a high amount of strain. So, it has a lot of strain energy apart from this interface. Apart from interface energy, that is surface energy, you have a significant strain energy which will oppose the deformations. So, these are positive contribution, whereas so that means what you need for martensitic transformation to take place, you need certain amount of supercooling, and this is the amount supercooling. And when you have a certain amount of driving force, this is the free energy or the driving force for martensitic reaction. So, if you look at the free energy composition diagram, here also it is shown, this is the free energy composition diagram of martensite, this is the free energy composition diagram of austenite at a particular temperature. Let us say this temperature is T0. Here, say look at this is for this particular composition C0, the is the composition. Here if you cool, it is possible to suppress precipitation. So, but this does not happen at this particular temperature. You have to undercool, and you can use your principles of what you can do is, it is possible to calculate this driving force, and the same way we worked out for precipitation process. This is the undercooling. So, this driving force is proportional to the undercooling. Higher the undercooling, higher is the driving force for martensite formation. And it is possible to draw superimpose on the iron carbon phase diagram this particular relevant portion of the iron carbon phase diagram, the temperature T0. So, this is a function of carbon content, higher the carbon content T0 is lower. So, also MS or MF. So, that means MS MF temperature should also be function of carbon content or composition of the steel. Higher the carbon content, lower is the MS, lower is the martensitic MF temperature, completion finish temperature, and lower is the T0, that is equilibrium temperature. Now, here if you try and apply exactly the same way, that concept of that nucleation process to get a say you can assume the shape of this nucleus to be a nucleus of a martensite plate to be an oblate spheroid. It has a radius, say radius is r and thickness is c. So, something you can think about a thin plate, something like this is a thin plate. So, this radius this is twice r and plate thickness is c. This is the plate thickness. So, then it is possible you can calculate its volume, you can calculate its that surface area with these assumptions, and which is shown over here. Say suppose in this particular structure austenite, this is an austenite grain. If a plate of martensite forms like this and shape being oblate spheroid, it is possible to calculate its volume, which is shown over here, multiply by the driving force free energy that which is a function of undercooling. Then there will be a strain energy associated with it, this will be positive. So, this will be volume multiplied by that strain energy, and usually the strain energy is a function of that the shape of this plate. So, how much is C over R ratio. So, this strain energy is equal to A is a constant times C over R, plate thickness over the ratio or over the radius. And then this is you have this new surface being created. So, pi r square is the top surface, pi r square is the bottom surface, to two thin surfaces are being created times the gamma, which is the surface free energy. So, if you write and then you go through the similar procedure, it is possible to calculate the critical size of R star, critical size of C star, as also that activation hill. Now, if you find in this here, if you substitute the value, I have left this to you to derive this expression, and if you find this out, there will be an activation hill. So, you have an activation hill which must be overcome for that martensite transformation to take place, and people have calculated this activation hill comes out to be too high. So, then the doubt arises that are there is nucleation is important, how does nucleation takes place if the activation hill is so high. So, some people thought is possibly these nuclei are pre-existing, and only when it it is growth control, and when that growth is very fast. But nobody has seen today even until it is extremely difficult to prove also experimentally. There is no experimental evidence of pre-existing martensite nucleus. So, with this little background on the nature of the deformations that can take place in iron carbon system, it is possible to understand what structural changes that take place in some of the common heat treatments which are given to steel. And mind you, these heat treatments people knew about it much before our understanding that mechanisms, the microstructural changes that take place much before that all these were known, and these people learn by experience. And in this case the cooling rate that one adopts is not isothermal cooling. In most cases you will heat it to a particular temperature, and then either you quench in a medium, say water, or you let it cool in, take out the sample, keep it in air. In that case the sample cools in air. So, that means the temperature of the job that to which is being given the heat treatment changes continuously. And how do you interpret the transformation that will take place during such continuous cooling? And this can be inferred from the isothermal transformation diagram. Let us see how this is done. So, most these commercial heating these heat treatment processes, there will be three distinct steps. So, one is you heat to a particular temperature, and then you keep the sample for a certain length of time, so that it develops a homogeneous structure, and then you, so that is called as that step is called as soaking, and after it is soaked, you know, you are sure the structure is homogeneous, then you cool. This is the third stage. So, these are the three steps on any heat treatment process, and this cooling can be done in two ways. We talked about this isothermal cooling. So, here you, this is the temperature where sample is heated, then you quench it to a bath maintained at temperature T, and then you keep it for sufficient length of time for the transformation to be completed, and then you, it does not matter whether you cool slowly or fast, the structure does not change. So, this is one kind of a isothermal transformation. Now, normally if you take out a sample and leave it in air, so it will cool something like this, and usually these temperatures are plotted against logarithm of time, because time scale can be quite large. To represent the way the temperature decreases, often we use logarithmic scale. So, in that case a constant cooling rate will appear like this. And in fact, this is shown a little more critically here. So, one can look at what are the continuous cooling laws. So, we can think of two types of cooling laws. See, one it could be, say, cooling rate is uniform, another is a normal that is a natural cooling that takes place. When you take out, we know that any metal, if you heat it to a particular temperature, take it out, keep it in air, let it cool. So, in that case initially the cooling rate will be fast, and later on as it cools down, cooling rate becomes slow. As the temperature of the job decreases, cooling rate decreases, and which is actually mathematically it is represented like this. So, one way could be a constant cooling rate. Here either you have to mechanize a device so that that heat transfer rate is constant, and you can maintain a constant cooling rate. Otherwise, if you allow it to cool naturally, in all probability it will follow this kind of a cooling kinetics. This is the that is decrease in temperature will be proportional to the temperature difference of the this is the surface temperature, this is the surrounding temperature, and heat flow within the job will follow the normal conduction rules. So, let us not go into the details of this. To sum up, what we can see that if you plot this cooling rate, if you plot this temperature against time, then this is the constant cooling rate, this is the Newton or natural cooling rate normal, that is with decreasing temperature cooling rate goes on decreasing. But if you superimpose this on a temperature against log T, the shape of the curve may look like this. Now, let us try and find out what are the common first let us see what are the common heat treatments we are going to look at. Now, 3 common commercial heat treatment processes are listed here. One is annealing, second is normalizing, third is hardening. And we will see when you harden, since when martensite forms, the surrounding lattice will undergo tremendous amount of strain and which is accommodated through slip or twin. So, this introduces lot of strain, and so therefore, the structure is highly unstable and often it is susceptible to cracking. So, it is given a treatment called tempering. And here that heating cycles which is shown here, say normal common is you heat it to an austenizing temperature and you keep it, and this let us say first we are let us consider eutectoid steel. So, heat treatment temperature, that austenizing temperature irrespective of whether it is annealing, normalizing or hardening, the temperature is around 30 to 40 degrees centigrade above the eutectoid temperature. And here this is the soaking time, this is heating cycle, this is the soaking cycle. After the structure has become homogeneous, the temperature is also uniform, then one way you can cool extreme, you quench in water, very high rate of cooling, then you this is the treatment called hardening, and after hardening it is given a tempering heat treatment where you raise the temperature to a level some say 100 degree, 150 or 350, but certainly much lower than the eutectoid temperature. At that temperature some amount of transformation takes place, some amount of ductility is restored, brittleness goes down, and then you can quench. So, this part is called tempering and this quenching is the hardening. So, this red line represents hardening and tempering. Another case which is where you take out the sample and just leave it in air. If you allow it to cool in air, still air, so this is the cooling rate. Say we assume that we are plotting it as a straight line, thinking that we are able to maintain it, which is never. So, so even if it is cooling like this does not matter. So, this case what we say, it is relatively much slower cooling than the cooling rate that you adopt in hardening. So, this is called normalizing. And extreme slow cooling, what you can do after soaking, you can just switch off the furnace and let the job cool in the furnace. Excuse me. So, in that case furnace cooling, you get this type of a heat treatment where the job is cooled in the furnace is called annealing. So, obviously you can see. So, this is a case of hardening, you get the maximum hardness. In air cooling, the type of structure you will get an intermediate structure, and here you will get the coarsest structure which will have the lowest strength, but good ductility. So, as you go down you can see from annealing to normalizing to hardening, strength goes on increasing, whereas the ductility goes on decreasing. Now, a quick look at that how you can draw the cooling curve or infer the cooling that CCT diagram from an isothermal transformation diagram. So, here you see this is here we have an isothermal diagram which is superimposed, and let us consider for eutectoid steel. Now, in this case we can always think of that isothermal cooling, this continuous cooling, this is the continuous cooling path. We can always break it up into steps like this. I have drawn a very coarse step, it can be made even finer. Now, what happens when you are cooling, say suppose as you cool it, say if you are cooling, this is the hold time. So, here the hold time at a particular temperature is quite easy to find out, and what you can do, if you look at, this is the hold time here and here this is the transformation. So, it remains for a certain fraction of the time. So, a part of this transformation has taken place which is not visible, but that hold time is proportion to a part of this hold time. If you would have kept it that long, transformation would have started, but you have not kept it that long. So, a part, and if we say that this is cumulative, here this fraction, say we say that this is a T s 1 and we kept it at time t 1. So, this is the fraction of time it had spent here. Similarly, when it comes here, it remains for this. So, here your total time is this. So, what you can think about, if you can sum up. So, here this total time over this is the time fraction which it spends at particular temperature. So, what you can split this up into this kind and try and find out when this reaches 1. This is how it is possible to convert this isothermal diagram to a continuous cooling diagram, and obviously what it comes, obvious that during continuous cooling transformation will not take place once this line intersects this. You have to cool it still further. So, which is shown. So, this is the start of transformation in continuous cooling, and similarly there will be a finishing line. So, therefore, the CCT diagram will be this part of the diagram, continuous cooling diagram will be entirely different, and we will it is also extremely difficult that Bainitic transformation does not take place unless in plain carbon steel, unless you cool it isothermally below the nose. So, this is a problem. So, therefore, in most plain carbon steel diagram, the CCT diagram, if you look at, you will find the diagrams are like this. So, only the Pearlite portion, this is austenite, here you have ferrite plus cementite lamellar structure called Pearlite. So, upper end you have coarse Pearlite, below you have fine Pearlite, and on this I have superimposed just schematically different types of cooling rate that you can think about. If you water quench, that cooling rate is very fast, depending on whether you are quenching in water, still water, or agitated, I mean the bath is agitated, you can get a substantially very high cooling rate. You can get this kind of a cooling rate, and this is the critical cooling rate. If you cool faster than this, you can suppress diffusion control transformation, you can suppress Pearlite transformation. So, this is the critical cooling rate, and this is average, that normalizing when you do the air cooling, maybe your cooling rate is follows like this. Mind you, these rates are approximate, these rates will also depend on the dimension of or size of the job that you have, and in case of annealing, when you do furnace cooling, the cooling rate is as low as or even lower 5 degree centigrade per second. So, therefore, what you can infer now, what will be the microstructures or how will this microstructure look like, or normally when you cool a job, it is quite interesting. It is if your job has a dimension, when you cool it, it is always not possible that every point will cool at the same rate. Possibly you will find even if you quench a job in water, the surface will cool very fast, whereas the center, the cooling will be controlled by the way that heat can be extracted from the surface as well as through conduction in the job, which will therefore depend on the size of the job. So, therefore, what we can get is possibly a gradation of different types of structure you can get at different place, and which is pictorially shown over here. Suppose this is a job, you heat it, it is a red hot, and now you quench it in water. If you put it in water, you will find that the surface is the cool down fast, but center is still hot. The top surface is exposed, so which is also red hot, the side cools. So, therefore, what you will have? You will have, after that, if you take a section and try to look at the microstructure, what you will find? The center surface will cool very fast. It is possible the surface you will get a cooling like this, which avoids the nose of the curve, whereas say which is shown over here. Say surface, this is the nose, it avoids the nose. So, surface you will have martensite, but in between what will happen? There can be some right at the center, which will be totally pearlitic. Surface will be totally martensitic, and in between you can think about certain cases where you will have pearlite forming, that is pearlite which are fine, these nodules of pearlite which are made up of, they will to start with they will all form along the grain boundary along these triple points. So, they get nicely marked. So, if you take out this is the job. If you take a section, look at the microstructure from surface to the center, you will get microstructure will change. On the surface you will have martensite, on the center you will have totally pearlite, and in between somewhere you may find a structure like this. So, which marks delineates the prior austenite grain boundary, and in between after this portion is martensite. And normally when you develop microstructure, martensite is very difficult to etch. So, these will appear bright, whereas the pearlite nodules, they will be so fine, they will appear as dark nodules. So, these nodules mark these grain boundaries. So, what it shows, this austenite grain boundary, the prior austenite grain boundary you can find out by such a gradient quenching technique, or this kind, or any heat treatment process. It is possible, you take a section, it is possible to find out austenite grain size. If you look at it, you can also think of a gradient quenching. Say suppose if you heat a sample like this and quench only one end like this, and when it comes out you take a section, here also you will exactly get the similar structure. Possibly here you may get, by modifying this, you may get a much quench end, this is your cooling rate, whereas the other end, distant end, you have this cooling rate. So, this is a way you can devise an experiment, and in fact, this size of this prior austenite grain size is of quite important in any commercial heat treatment process. As we will see, if the grain size is very coarse, in that case you get coarse austenite plates. Also you get coarse martensite plate, and when you quench, this structure is often brittle, and in fact you have to design your heat treatment process in such a way that martensite develops in a relatively fine grain austenite structure. In that case, quench stress susceptibility to cracking will be less. So, therefore, what it means, and the size of this austenite grain size can be controlled by controlling the austenization process. And in fact, this is quite in fact the first stage of any heat treatment is the process of austenization, which is shown here. This is austenization. See, all annealing, normalizing, hardening of an eutectoid, heat it to the eutectoid temperature, cool differently, and these are the structures, and I will leave it to you to find out, draw the microstructure. Here it will be annealing coarse pearlite, here it will be fine pearlite, and in case of a hardening it will be martensitic structure, and this will be the hardest, it will have maximum hardness Rockwell, this will be intermediate hardness, this will be the minimum hardness. And this is a quick look at that summary. If you can look at this annealing, normalizing, hardening, which are the characteristic structures which are listed here, and maybe next class we will look at it a little more detail. Also we will look at the process of austenitization, which is quite important. So, therefore, to sum up today we looked at martensite structure and its habit plane, why it develops or forms on certain specific crystallographic plane. We also looked at continuous cooling process and CCT diagram. We also seen the relationship between TTT and CCT and introduced the 3 different or common heat treatment processes. Thank you.